All right, we should be on this page here. We're going to talk about rectangles and parallelograms today, but we're going to switch gears a little bit and start talking about area. Yesterday we talked about perimeter and like circumference for a circle, which is basically perimeter, but dealing with a circle instead of like a polygon. So now we're going to kind of switch into talking about area. That doesn't mean though that we're never going to do perimeter again. In fact, on a lot of your worksheets, after we talk about area, you'll do some problems that involve finding area, but then it'll also be finding the perimeter of the shape as well. So you'll have to maybe sometimes do both. But we're going to focus primarily today on just area. And we're going to talk about rectangles and parallelograms because they kind of go together as two shapes. They are really similar to each other in their formula, so that's why we're kind of lumping them together today. First of all, if I just take a look at this picture here, I've got 3 rectangles. They all look like they're the same to me, but they're all labeled a little differently. Go ahead and just take a minute and look at the labels and the way that they have those rectangles kind of all situated up there. And just what do you notice about the length, the height, the base? Anyone notice anything as they look at those 3 shapes there?
You could put like the length and the width and the base anywhere.
You could put the length and the width and the base anywhere you want. Yeah, they're pretty interchangeable, it seems. Especially on like the last 2 where it says base and height. They kind of have those switched around on the 2 rectangles. And so we could do the same thing with like length and width. Now, maybe when you guys first learned about rectangles, you spend a lot of time talking about the length and the width and like, what does that mean? Today and like going forward, I may not refer to it as length and width anymore. I might more so just say base and height because that also will play into parallelograms. And so I like to just kind of use common language when I'm talking about all these shapes. That way we don't have to try to remember a whole bunch of different formulas. But yeah, I agree that it looks like the length, the width, the height, the base, like they could really be interchanged anywhere. But when you think about a rectangle, think about what we learned in first semester when we did that whole unit about quadrilaterals. What do you know is happening in the corners on a rectangle? They're 90 degrees. So when that base and that height, or when the length and the width kind of connect to each other, they're hitting at those 90-degree angle corners. So that's something that we're going to want to keep in mind too. When my base and my height connect, they have to be perpendicular. So down here where it says a base and a height must always, we're going to fill in be perpendicular. Remember, perpendicular just means that would have a 90-degree angle. So in order for you to have a base and a height, they have to be creating a 90-degree angle here. That's going to be more important when we start talking about parallelograms today. Rectangles are kind of already built to have the perpendicular factor already in it because they all have those 90-degree angles in the corners. So when I look at a rectangle, my dimensions on the outside should already just be my base and my height. Now remember, to find area, you would be figuring out all the space on the inside of the shape. So for example, when I look at these ones down here, if I wanted to know what the area of this first one was, I would need to know like how many squares are there in my shape. So I would count up all these squares if I wanted to go about it the long way. Okay, you'd count up 1, 2, 3, 4, all the way up to 12. But if you know the dimensions, what do you just do with these 2 numbers to get that same answer of 12? You just multiply them. That's a shortcut. We don't have to add up a whole bunch of squares. Okay, now that we know what our length and our width are, or our base and our height, we can just multiply the numbers together. So you would take 6 times 2, which you guys said was 12. Now, do you guys know how to label area? Centimeters squared. Okay, remember yesterday with perimeter, it wasn't a fancy label. It was just something like centimeters. Now we're switching into area. So all of our labels need to have that little 2 of an exponent because we're talking about the dimensions, length, and width, and then everything in between them. All right, so let's do the other ones here. These should be pretty fast now that we know what these formulas look like. How would you guys find the area of the second one? What are you multiplying? 8 times 4, which is good. And then the last rectangle? 5 times 1, which is just 5, and still centimeters squared. Again, you could still be counting all the squares. That last one has 5, that middle one has 32 squares total, but it's faster to just multiply instead of having to count one at a time. Now, area of a rectangle, like I said, most of the time you guys probably learned it as length times width. I'm going to change it a little bit here today and just say base times height to keep it consistent with what we're going to see for a parallelogram. Now, like I said, a rectangle already has that 90-degree angle, that perpendicular thing that we have to have in order for us to know that we have a base and a height. Parallelograms are built a little bit differently. So if we look down below, we're going to talk just briefly here about the parallelogram. Now, it says that this parallelogram formula relies heavily on the area of a rectangle. It means that they're going to really be closely related to each other. We want to find the area of the parallelograms below and look for a connection between the area of a rectangle and the area of a parallelogram. Now, if you look at these ones, like I started out with the top, counting squares, this is a little bit different. I could still count squares. Like in the middle area, like these kind of chunks here, those are all 4 squares. So that'd be really easy for me to count. But as you get up towards these other parts of the parallelogram, it gets a little bit harder to count these squares because they're like sliced by that side. You don't know if it cut it directly in the middle, if it's like a fourth of a square, a third of a square. It's really hard for us to tell when we're on a graph like that. Is there a connection though between maybe the partial squares up here and something down here at the bottom?
You just put that part of the square down there.
I could take all of these partials and put it right down here?
Yeah.
And what shape would I be making when I do that?
Rectangle.
A rectangle. Okay, so if I just think about what you said there, I've moved all these partial squares. If I just shift that whole top down, so even just take this corner and move it down 1 to right here. And move this corner down 1 to right here. Move all those partials down below like you said. You just created a rectangle. Now, what are the dimensions of this rectangle? 3 by 5. So if I wanted to find area, wouldn't we just multiply again? And we'd get what? Well, do we know it's centimeters this time? No, we don't. But I like that you're labeling it because we do need a label. But in this case, I don't know what they're measuring these squares in. It could be centimeters, it could be inches, it could be feet, it could be miles. So when we don't know, we say units squared. Just if they don't give a label, that doesn't mean you don't get to label, okay? That doesn't mean that you're exempt from having to label the answer. We still just can give it like a generic name like this, and then that could get replaced with whatever. Okay, I like that. So move that down, make it into a rectangle. It makes it really easy for us to figure that out. Now look at B. Could you do something similar with this one? I've got a couple full squares in the middle, but then I've got some partial squares on the other sides. Could I move those somewhere too, like we did the last one? Where would you move them this time? To the left or to the right, right? I could go either way, but if I maybe move it to the left, this would be your rectangle you're looking at. So I'm taking kind of those partial pieces over there and I'm shifting them to the left. You could also take the left-hand side, those partial squares, and move it to the right. You'd get the same rectangle. What are your dimensions this time? Ooh, careful, not 6 by 1. 4 by 1. Because remember, we did move those squares over, those points over, so we're not going all the way to the end of that corner anymore. So what's the area here? Good. Okay, and what about this last one, C? We could still move squares if we wanted to. But maybe also, let's just kind of zoom out here and think about this for a second. When we were making those rectangles, like on this first one, when we moved this down, This side really was not affected at all when I moved that rectangle down, or the parallelogram down to create the rectangle. This was still 3. This, though, was affected a little bit in that it got dropped down and I saw that it was 5. Was there somewhere else in my original parallelogram where I still could have gotten the 5 from without having to move it down?
How many squares across to go?
How many squares, like from this side to this side, you're saying? Yeah. If you counted like from here across to here, isn't that still 5 squares? So that would be like another way to think about its height. Instead of moving this thing down into a rectangle, we could think about the height being on the inside of the shape. And so if you go from here to here, it's still 5. We could do the same thing with these other ones. If I go from top to the bottom, that's 1. Or if I go left to right, that's still 4 squares. So think about that on C. This side that's going up and down is 3. So that's easy for me to see. How wide is this parallelogram? 2. And you have to go to its like widest point. You can't go up to like the tip little corners and call that your height because that's not relative to the whole shape. So if you go from this dot all the way across, to this space here, that's 2. So what's the area of this one? 6. And still units squared. So I guess the question now is, do you think our formula is any different for a parallelogram than it was for a rectangle? We did the same math, didn't we? So my area is still going to be base times height. And that's why I said earlier that I'm going to start saying base and height instead of length and width, because my rectangles and parallelograms, they act the same way. We do just have to be careful on parallelograms that we're using the correct length for the height. Okay, so if you guys turn your page over, you're going to see at the top here that we've got a couple of shapes. Okay, now these are all parallelograms. So we could find like the base of it because we could call like the flat side the base, but we've got some slanted sides too when we're dealing with the parallelogram. So I have to figure out the height, okay? Because I'm going to come back up here to my formula and I'm just going to write a little note here that says your base and height still have to be perpendicular, just like they were on a rectangle. That means I still need a 90-degree angle. So when I'm looking at these ones down here, I need to draw the height in. Kind of like what I was talking about on those grids. You can go base to base, you can go across the shape and create a height. So we can still do that here. So if we look at these ones down below, there's more than one way that you could draw in your height. You just have to be careful about where you put it. You have to be connecting opposite bases to each other, or opposite sides need to be connected. You can't go from like here to here. That's not the height of a parallelogram. That's not giving you the full length from base to base. So we couldn't do something like that. Okay, now it might be a little hard on this one to connect like the shorter 2 sides because this one is so slanted. It's able to be done, but it might be a little bit difficult for you to do or draw in perfectly. So I would maybe go the other way with it. And what I like to do is at the intersection where the side slants, I like to start, so like at this corner here, I like to think about that side if I drew it straight down to the bottom and created a 90-degree angle. Almost imagine that you're drawing in a triangle on the edge of that shape. That's going to be my height. That's not the only place you could have put it though. I could have put one on the bottom and done the same thing. I could have drawn my height on this side instead. I'm still making like a little tiny triangle. Like I said, I could still do it on the other bases. Those ones just might be a little bit different looking, or your height would be going in a different direction. But then that would also change your perspective on where your base is at. So I want you guys to take a second here and draw in 2 more heights, one for B, one for C, just to kind of practice how you would connect base to base. Imagine you're drawing little tiny triangles. Make sure that there's a 90-degree angle box labeled on your height. Okay, why don't you look at someone at your table, see their heights, and see if you agree with what they drew. Okay, I have mine up there. Just because I put mine there, though, doesn't mean that's where yours has to be. So if you drew it in a little bit differently, still connecting base to base, still making that 90-degree angle, then you should be fine. Okay? I usually try to just imagine where a little right triangle would be at in one of those corners to get my height drawn in. So when you're looking at a parallelogram, be really careful because I just want to show you, like on this middle one, sometimes they'll draw a height like this. So like they could call this your height and this is still your height here. But when they do it on the outside like that, notice how I use like those dotted lines? That's sometimes going to be in your pictures, and it can be a little confusing on problems where they want you to find the area and the perimeter, because students will mistakenly think that those dotted lines are part of the shape when they're doing perimeter, but they're actually not. Those dotted lines were drawn in additionally to create a height. So the height could be useful, but it's really not going to do you anything when you're talking about perimeter unless you're trying to find a missing side. So be careful when you're looking at these pictures because you might see that drawn on the outside of a shape. All right, what we're going to do now is do some problems here. We're going to find the area of these rectangles and parallelograms. You should hopefully start to be able to look at a shape and know what you're working with. So when you look at this first one, is this a rectangle or is this a parallelogram? It's a parallelogram. Okay, you should be able to tell that because it's a little bit slanted. It's not square at the corners, so it can't be a rectangle. So when you look at the labels on here, what's your base and height? 8 and 10 is your base and height. So 8 your base, 10 is your height. I'm just going to label those. How would we find area? Multiply them. So what is 8 times 10? 80. And what's my label? Good. Centimeters squared. Okay. What's what on this next one, number 2? Well, first, are you dealing with a parallelogram or a rectangle? Still a parallelogram. Do we have the base and or the height? Do you have either piece? What's the base? 11. So I'll put a little b by 11. But we don't have the height because the height would be on the inside where that 90-degree angle is happening. Okay, but look at what's over here. What kind of triangle is this? It's a right triangle. Now, what else are they adding in on that right triangle for you? 45, which probably means they're wanting you to pull back on some prior information about special right triangles. The 45, 45, 90 triangle. Does anyone remember, I'll just draw out a 45, 45, 90 over here, what the pattern was with the sides? The sides were the same. The legs were the same, so we called those like S and S. And do you remember how we labeled the hypotenuse? S times the square root of 2. So now if you look at the right triangle that we have on our parallelogram, they're giving you that hypotenuse side. They're saying that this is 5 square root of 2. So that would match up with this side. So what does that make just these two legs? 5. Because you just dropped the square root of 2 for this one. So this height is equal to 5. Now, can you find the area? What do we get? Good, 55 centimeters squared. Very good. Questions on those first two before we go on to the second two? All right. Let's talk about this one. Does anyone have an idea how we could approach this problem?
The dash on the right side is 6.
Okay, so we know this is 6. Good.
The smaller one is 2.
Okay, because you took 8 minus 6, so this little side's 2. What would be the bottom then? 6. Okay. That would be really helpful to label all of those sides, especially if they wanted you to find perimeter, because we would add those all those up. But I want to find area of this shape. Anyone have a plan of attack? How would you do this if you had to do it on your own? Okay, I heard two things. What did you say, Brady? Do you mean a dotted line going this way? Okay. What were you saying, Leah?
To multiply all the numbers.
Okay, we don't want to multiply all the numbers for area. You would actually add them all for perimeter. But I like the dotted line idea because you're splitting it into two smaller shapes that are maybe easier for you to work with. Is that the only way you could split that shape up, though? No, did anyone maybe want to go this way with it instead? Maybe make it into like two rectangles. That would work too. Okay, there's actually another way we could handle this, but I'll save that for a minute. Let's talk about how we would do this one. So how would you find the area of like this half? 6 times 6, because it's a square now, so that's going to be 36. And then what are the dimensions of the rectangle on the left side? 6 by 8, which is 48. And then what do you do with those two numbers? You add them. So what is 48 plus 36? 84 centimeters squared. Okay. There's another way that someone in my first period class said that they thought of it as. I'm just curious, does anyone else out there have a thought? Yeah, Brady.
8 times 12, and then subtract 12. Or, yeah, subtract 12.
Okay, is that what you were going to say,
I was
Miles?
gonna do 12 times 8 minus 2 times 6.
So he's saying 12 times 8 minus 2 times 6. Is that what you were kind of along the lines of? So when they say 8 times 12, what do they find in the area of?
Big rectangle.
The-
Connected that bottom right part.
Yeah, so if I drew in like this, and they do 8 times 12, they're talking about the big overall shape. Like they made it into one big giant rectangle. And this comes out to be 96. But then they also said, well, because we did this and we added on this piece that's not actually included on my original shape, I have to subtract it, you said. And it's a 2 by 6. And what's 2 times 6? And so what's 96 minus 12? Still 84. We got the same answer, didn't we? So there's actually multiple ways you could approach this. The other one I had mentioned earlier is that first hour also said, let's draw a line like that. And they found the area of those two rectangles. They still got a final answer of 84. So there was 3 different methods that we've talked about on how to do that problem. But you do want to split it apart or think of it big picture and then subtract away what you've added on. All right, we've got one more. What shape are you working with this time? Rectangle, because it appears to be a little bit more square at the corners, which means I know then that there's got to be a 90-degree angle here. Do we have our base and our height? Do we have either of them? Which number is useful for us for area right now?
The 5.
The 5. So I for sure want to use this. Now let's just call that our base, okay? But it could be your height. It doesn't really matter. How do we find the other side though? Because that would be where my height is. Pythagorean theorem. And if you remember yesterday, I mentioned Pythagorean triples. I talked about like a couple cases, and there was one that I said was going to show up a lot. Well, guess what? Here's the first time we're seeing it. Does anyone remember the pattern I talked about? 5, 12, 13. So I have a 5 and a 13, which means the height has to be 12. Okay? And I said yesterday you're going to see 5, 12, 13 a lot in these next couple of units. So this is time number 1. Start making your tallies because we're going to have a lot. So we would take 5 times 12, which is what? 60. And then it would still be centimeters squared. Very good. All right. That's it for notes. I'm going to get you guys your homework.